I'm going to talk a few minutes about error tolerance in system design. So, what is error tolerance? Let me start by an example. You're browsing a website and something goes wrong. You definitely don't want your whole computer to crash, right? Or a more tangible example, you are on the road driving your car and all of a sudden you get a flat tire. You definitely don't want your car to stop all the way, right? Your car manufacturer doesn't want that either. So they design your car in a way that it is still operating, but it may slow down or something. They call it graceful degradation. So how do you design your system to degrade gracefully? There is a highly common way in the field of ergonomy that starts with a hierarchical task analysis, or HTA. HTA is basically a goal-based system design that is used both for machine or human performed tasks, in which you break down your main goal to some hierarchical sub-goals. There is a methodology within HTA that is called Sherpa, that is for detecting or predicting the errors. Sherpa stands for Systematic Human Error Reduction and Prediction Approach. Sherpa categorizes each task in one of the five types that are as follows: 1. Action, 2. Retrieval, 3. Checking, 4. Information communication, and 5. Selection. After putting your task into one of these five categories, you can tell which error is credible for each task. For example, in action, you may call errors such as operation too long, too short, mismatch, operation in wrong direction, and so forth. After you categorize your tasks and identify the possible errors, you need to know how to deal with any of those errors. One approach that could be used in error tolerant systems is to accept a wide range of inputs and have a strategy to deal with any of those. For example, your output might be very negative, negative, zero, positive, or very positive. These values are basically the cost of error, and you can multiply them by the probability of the failure, and the results should tell you how to deal with the output with those values. The only problem is it's not always easy to calculate those values. For a smaller system, a subject matter expert can tell you how severe each problem is, but for a bigger system like a big software, we have a different story. Since there are hundreds or thousands of different states, there should be an automated mechanism in place that does the timing check, code checks, reversal check, structural check, and so many other checks at software runtime. In order to recover from an error, there should be an additional component that either corrects or replaces the faulty component. This concept is called redundancy. For example, in bigger aircraft, we always have a co-pilot that helps with double-checking some of the procedures and operations. Or in hardware or mechanical devices, the component degrade over time, so there should be a spare component to replace the faulty component. In software, the situation is slightly different. Software doesn't degrade over time, and the failure are mainly due to the activation of specification or design fault by the input sequence. So the fault might happen right the first time that the relevant condition happens. This makes the reliability of the software depends on the environment that generates the inputs. But still, many of the software techniques are leveraging the hardware redundancy methods. One example would be single version technique that adds additional function to one software module that are not necessary in a fault-free environment. These additional functions monitor the action to detect a fault, isolate it, and prevent its effect to spread throughout the system. After conducting the check, software structure design can accommodate the recovery steps. Some common fault containment techniques are software modularization, partitioning, and system closure. If the fault containment is implemented properly, some of the following recovery techniques might be affected. First is exception handling, which is the interruption of the normal operation to handle abnormal responses. Another technique is checkpoint and restart, or backward error recovery. This method is based on the fact that some of the error might happen because of an input that appears only for a short period of time. So if you start over, that input might not exist anymore. The third method is process pair, in which two identical versions of the software operate on separate processors. The first processor executes the program and sends the checkpoint information to the secondary processor, and if fault detected, it delegates the task to the second processor. At this point, the first processor starts the diagnostic, and if it could recover, it becomes the secondary processor in the next task. There are other sets of techniques that are labeled as multiple version techniques. Multiple version techniques are using different teams, different coding languages, or different algorithms to maximize the probability that all the versions do not have common faults. There are different ways of deploying this method. Here I introduce two of them. One is recovery block. In this method, one code base gets executed and the acceptance test unit checks the output. If the result is not acceptable, the switch sends the operation to another software unit. The second method is n-version programming. In this method, n versions of the software execute concurrently, and the selection algorithm decides which of the answer is correct and send it as a result of module's execution. Okay, I end my talk here. I hope you found this quick introduction to error tolerance useful. Thank you.